Before I do a design review of the 6502 CPU board, I wanted to talk about an error that I had made in the original design. I'm now on version 1.2, and I got here because I made a design mistake. And the design mistake is one of those educational things I want to teach everybody. So I'm going to show you the specifications of a particular part called an AT-Tiny 2313. And I've used this part a number of times in other projects. It's a small 8-bit AVR microcontroller from Atmel. And it's got a lot of very nice features to it. And when I was designing this 6502 project in the CPU board, I wanted to create a page register so I can page in and out multiple pages of an EEPROM. And so I thought, I'll just use this part that I have a whole bunch of. And I went to the specification sheet. And the specification sheet says, this thing will operate through 20 megahertz. I went, score. And I go down a little bit further into the specification sheet and it says, but you have to run it at 5 volts. No problem. So as I go through the specification sheet kind of quickly, I missed something. And this is one of those lessons in life that you learn, and I wanted to share it with you. So the maximum frequency that this part will operate using its internal RC oscillator is 8 megahertz. And I didn't figure this out until I made the CPU board, put all the parts on it, and wanted to program this chip to run at 20 megahertz. Turns out, in order to run it at 20 megahertz, you need to use an external crystal. So I wanted this to be one of those life lessons that I shared with everybody so that you'll find this cautionary tale and don't do what I did, which was to read the specification sheet very quickly. So now let's move on. The 6502 CPU board schematic review. Before I review the schematic, I feel it necessary to review the design tools I use. I use Altium Designer for creating my printed circuit boards and schematics. The reason I use Altium Designer is because many of the hardware engineers I have worked with in the past used Altium Designer. When we would collaborate on a project, they would send me their entire project. This gave me a copy of the schematic and printed circuit board. I could then use the tool to locate test points on the printed circuit board that I would need to use to validate and verify that my code worked on their hardware as designed. Before I continue describing my process, I wanted to make you aware of free versions of schematic capture and PCB software. Here are some links for you to look at those products. The steps I use to design a product are the same. After I have a design goal, I select the parts I want to use. I collect all the data sheets and store them in a common project directory. The next step is to create library parts to use within Altium. I first create a footprint, which is used on the printed circuit board layout. I also create a schematic block. A schematic block is where I organize the pins into a logical fashion that makes sense for the schematic. Most parts are organized by internal circuits, which cause the pins to be grouped by circuits and not by functionality. That's why the schematic block is so useful. If you look at the 6502 CPU block, you'll see I've organized the pins as follows. On the right-hand side are data and address buses. On the left-hand side top are the control pins used in this design. On the left-hand side bottom are the control pins that are not used in this design. Some of these control pins will be used when I verify timing or decode the data stream back into assembly language. More on that later. The first set of lines we're going to look at is the address lines. You'll notice that we go from address A0 through A15, which is a total of 64K of addressable space. Then we're going to look at the data lines. We go from D0 through D7, which makes that an 8-bit bus. The other pin to look at is the RWB line. This tells the direction of the data flow either to the processor or from the processor to the memory device. So if RWB is high, we're reading from RAM or ROM into the processor. If it's low, we're writing from the processor into memory. That would be SRAM. One of the design goals is to be able to program the EEPROM while it's in circuit. Fortunate for us, the 6502 has a pin called bus enable, or BE. What that does is when it's low, it takes the data bus, the address bus, and the RWB line and places those lines in a high impedance state, which is effectively removing it from the circuit, allowing us to control the address, data bus, and the RWB from the programmer. The initial design of the 6502 project, we added 12 connectors to connect to external devices such as a keyboard, digital input, digital output, etc. Plus a 13th connector which connects to a dedicated port that communicates with the Z80 interface. It is an interrupt controller chip which connects all 13 ports to a single interrupt control line, IRQ. When an external device has data it wants to send to the CPU, that device generates an interrupt, lowering its interrupt request line to the interrupt controller. The interrupt controller then lowers the IRQB line to the processor. What this does is it stops the current execution of the 6502 main loop and calls a special function to handle the interrupt called an interrupt request service routine. It is the responsibility of the interrupt service routine to communicate with the interrupt controller chip to get the number of the device that has data for the CPU. The interrupt service routine will then in turn talk directly to the device or port that has data for the CPU. Once all the data has been processed, the device that caused the interrupt will raise their interrupt request line, which in turn causes the interrupt controller to raise the IRQB line to the CPU. The CPU will exit the interrupt service routine and continue executing code where it left off prior to the interrupt request. The reason for the interrupt controller is that it allows us to multiplex many devices and ports to a single IRQ line. Non-maskable interrupt. So basically what a non-maskable interrupt is, the CPU runs in its normal state. Then an interrupt comes along and you're in the middle of an interrupt service routine. Now you have a catastrophic problem. There's no way if you're in the middle of an interrupt service routine to tell the interrupt service routine that you need to exit to handle the critical service problem that you could probably monitor within the main loop. That's what the non-maskable interrupt does. It says execute no matter what else is going on because this is a critical function. In my design, I have elected not to use it at this time, but I have brought the pin out to a test point so that if I do have something that I want to connect to it later on, I can wire it in. The ready line, noted as RDY. The ready line is an external signal or input to the processor to tell the processor to go into a wait or paused state. Why would you need to perform this operation? The reason is timing. Some devices that are connected to the processor may not be fast enough to meet the CPU timing requirements, and the data transfer between the CPU and the device may not be valid and may require a delay, allowing the device time to become stable. This device may be a memory or I/O device. In our design, the CPLD or control logic handles the ready line. Based on addresses, the CPLD could place the CPU into a wait state for X number of clock cycles, so the slow device has time to set up and stabilize its signals. With my initial design and the parts that I have selected, I suspect that all the devices will meet or exceed the timing that the CPU needs. However, this is based on specification sheets and not actual performance. Once I start testing the bus timing, I'll know for sure. What can happen if a part does not meet timing? You could get unpredictable results. CPU reset. The CPU reset is a signal that is used to start or restart the processor. Internally, what the processor does is to initialize itself and prepare to start executing code. This may take several clock cycles, but it's all handled within the processor. Once the processor completes its initialization, it will load the pointer located at FFFC/FFFD and start executing code. When we develop software, we're going to initialize our code so the pointer at location FFFC/FFFD points to our initialization code. More details on this later once we start developing software. There are two control lines, MLB and SOB, which I'm not going to be using. As I look over the schematic, I see that I placed the MLB in the wrong section. I say that because the pin is not being used and should have been placed in the lower section. Nonetheless, the MLB pin was created for multiple processor systems. Since our design is only using one 6502, we have no need for this pin. However, I can see using this pin in some sort of diagnostic capacity, as it's an indicator when certain instructions are being executed. The SOB pin, that pin is also a specialized pin, and it was used for fast input recognition. As I read through the specification sheet, it is not recommended for new designs. Since it becomes active on a low transition, I have pulled this signal high. In this section, we're going to cover the pins I'm not using in this design. I've already covered the SOB pin. The next set of pins are the PHI-1 and PHI-2 output pins. PHI-2 is the system clock to the processor. PHI-2 out is generated from the system clock, or PHI-2. PHI-1 is the inverted signal of PHI-2 out. When decoding data, PHI-1 out might be useful. Also, I'm not sure if PHI-2 and PHI-2 out are the same clock signal, or is PHI-2 out one clock cycle off of PHI-2. I say this because the documentation states that PHI-2 out is generated. This might be important when we decode the data stream. Another pin I'm not using for this design is the vector pull-up pin, or VPB. A vector pull-up pin is an output from the processor that indicates the vector location is being addressed during an interrupt sequence. That could be useful later on when I want to capture the interrupt service routines request, allowing me to isolate the ISR code. The next signal to look at is called the synchronize with opcode fetch, or SYNC. I like this signal a lot because what this signal does is it tells me the start of an opcode fetch. My plan is to connect a logic analyzer to the CPU board and capture the address, data, and RWB lines. From this information, I can capture the stream of instructions that the processor is executing, and I'll be able to decode the data stream into assembly language code, which can be used to verify the code I generated using the compiler is the same code that's being executed. Why would I want to do this? That's simple. When coding, you are writing software based on intent. This captures what really happened. What the sync signal tells me that we are fetching an opcode. An opcode is the instruction that the CPU is executing. Some opcodes require up to 3 additional bytes to complete the instruction requirements. When I decode the stream of data, I can look up the opcode and determine the next number of bytes that are needed to complete this instruction. This will guarantee that what I'm decoding is always valid data. CPU timing. There are only a couple of notes I want to talk about right now. One is that to achieve the 14 megahertz operation on the 6502, you need to use the correct version of the part, which is a -14, and I've done so. The second thing you need to do is to refer to page 25. There's a chart of performance, chart 6.3, and the chart talks about in order to run at 14 megahertz, you need to drive the part at 5 volts, and that's what I'm doing as well. The chart also discusses the min and max timing values. In combination with the min and max values, there's a timing chart on page 26, which outlines the timing needed for the part to operate correctly. Once we have built the board, I will write some test code. This will allow us to collect the data we need to verify that we've met these requirements. To capture timing, I'll most probably use my logic analyzer. I do have several MSO scopes with 16 channels that can be useful as well. They are the Agilent 100 MHz MSO, the Tektronix 200 MHz, and a 1 GHz MSO. Since we are running at 14 MHz, any one of these oscilloscopes will do the trick. Once I've captured the data, I'll post another video with the walkthrough and the results. For static RAM, I'm using a Cypress memory chip, the CY62256N-55. It operates at 5 volts. It is 32K by 8 bits wide, and it should run at around 18 megahertz, which is above the 14 megahertz that we're looking for. Since the inception of this project, my plan was always to use the SST 39S F040-55. The big reason is because I've used this part on other projects and already have the programming algorithm created and tested. The -55 in the part number means that it can run up to 18 megahertz, which is perfect for the design since we're trying to run up to 14 megahertz. The only difference in the chip I'm using from my original design to now is the footprint I used in my original design was the TSOP version, which became discontinued about a year ago. Since I only want to design surface-mounted boards, my only other choice was to use the PLCC version. When I went back to update my design from the TSOP to the PLCC footprint, I had noticed that when I created my original design, I had made a mistake in the page register. Instead of giving me 16 combinations of the page register using D0 through D3, I had only implemented 4 combinations, or D0 to D1, which meant I could only use a quarter of this part. Since my goal all along is to use the 16 pages, I redesigned the circuit to support the D0 through D3. How do I get to use the entire 512K? The processor uses A0 through A14 to select the 32K address space for the part. I have 16 combinations with a D0 D3 combination, so 16 times 32 is equal to the 512K that the EEPROM has. Control. This is the heart of how the CPU board works. In this section, I'm going to talk about the part itself, and in a later section, I'll go into more details. The part itself is an Atmel ATF 1502 AS-10JU44. It's a digital logic chip that takes inputs and generates outputs based on software programmed into the device. The part itself is made up of 32 macro cells and can operate at speeds up to 125 megahertz, which is well within our 14 megahertz range. I'm using the PLCC version. For the most part, most pins can be used as either inputs or outputs. There are a few pins which are dedicated,
but other than those pins, this part is very flexible. Atmel offers a toolchain which provides an editor, compiler, timing analyzer software, and a programmer. You'll need to purchase a programming module. As I have mentioned before, I like to design systems with flexibility and expandability. To achieve this goal, I've added several smart subsystems into the design. Using the AVR64DD32 chip, this is a very nice low-cost part with a lot of flexibility. I use this part in all the peripheral boards I've designed in this project, including the programmer. Why? Because this part is a complete computer. It runs at a max speed of 24 megahertz. It has 32 I/O pins. It has 64K of flash memory, 8K of RAM, and 256 bytes of EEPROM, which you can program to store configuration information if so desired. It also supports SPI, I2C, analog to digital conversion, digital to analog conversion, serial port communications, all with dedicated internal hardware. The part operates between 1.8 and 5 volts. This part is more powerful than my first computer. And you can write software to configure the part on how you want it to work in the circuit. One more thing, it supports UPDI, a single wire debugging port, so you can single step through your code as you develop the software for the particular solution you've implemented. Or you could set a breakpoint for a system-wide event like testing the interrupt controller.